Hey everyone, this is the Lazy Programmer, and I'm back again to tell you about my latest class, Artificial Intelligence Reinforcement Learning in Python. So what material are we going to talk about in this course? What I noticed in reinforcement learning is that there is a huge gap between what you learn theory-wise and what you do during programming. The theory is super abstract, so it's important to continuously think about how it actually applies to doing AI tasks like controlling a robot or playing a game. So to that end, we are going to actually start this course with some games. The first game we'll consider is slot machines. This picks up where my Bayesian machine learning course left off. We did the same example there in terms of click-through rates, but in this course you'll see the concept can be generalized to any kind of distribution. Slot machines, or the bandit problem, as it's known in reinforcement learning, will introduce us to an important concept called the explore-exploit dilemma. We'll discuss several techniques for making trade-offs between exploration and exploitation, including the epsilon greedy method, UCB1, and a Bayesian online machine learning technique. You'll recognize these from my previous course on Bayesian machine learning and A/B testing, since that is sort of a subset of what we're doing in this course. Reinforcement learning is all about trying to maximize a goal, or to use the terminology in this course, rewards. In A/B testing, the reward is a click on your advertisement or a conversion in your e-commerce store. So you see how that's a subset of reinforcement learning, where the game can be any game, not just running advertisements or e-commerce stores, and the rewards can also be anything, from learning how to walk to achieving the high score in a video game. The next game we'll play is a simple game by the name of tic-tac-toe. We're going to start very low level and come at it from the perspective of being a first-year computer science student. We'll ask ourselves the question, how would I code a game-playing agent that will never lose tic-tac-toe? As you probably already know, there are only a very small set of rules that you need to follow in tic-tac-toe in order to never lose. After going at it the naive way, we'll introduce the reinforcement learning way of doing things and code an agent from scratch that will train itself to play tic-tac-toe. In the following sections, we'll introduce the central framework for solving reinforcement learning problems, known as the Markov Decision Process, or MDP. MDPs will allow us to formalize and abstract all the concepts we learned about in tic-tac-toe so that they can be applied to any game or scenario in the real world. Then we'll introduce three separate but related techniques for solving MDPs: dynamic programming, Monte Carlo methods, and temporal difference learning. All these three techniques look very similar, so I think what you'll find interesting is that the hard part is actually differentiating between the three. In the last section, we'll do a little bit of a teaser and introduce what are known as approximation methods. The disadvantage of the previous three solutions to reinforcement learning is that they don't scale to large state spaces, or in other words, environments where you can find yourself in a large number of different states. The solution to this problem is to use approximation methods, and as you might have guessed, this is where deep learning comes into play, since neural networks are very good function approximators. While we won't explicitly cover deep learning in this course provides all the techniques required to plug in your deep neural networks into your reinforcement learning agents. Without the theory from this course, doing something like deep reinforcement learning wouldn't make much sense. My original goal was only to do a deep reinforcement learning course, but as I started to put together the prerequisites, I realized there was so much material that they would have to make up their own course. So that's what this course is. By the end of it, you'll understand the framework of reinforcement learning, how the three solutions work and the differences between each one, and how to use approximation methods to scale them up. And when we talk about approximation methods, you'll understand exactly how you can plug in deep neural networks so that when we start talking about deep reinforcement learning, we can just continue where we left off. So if you are interested in deep reinforcement learning, but you don't know where to start or even what the prerequisites are, then this course is the course you want to take. I'll see you in the next lecture.